Okay, as we consider the idea of the flow of charge, current, we have a term associated with that called electromotive force. Kind of makes sense. We need a force to move electricity around, right? But force, as you know, is based on an electric field acting on charges. So you think electromotive force would be electric field times charge? Well, not quite. So this term needs a little extra explanation. A better term for what is meant by electromotive force is energy per charge. As we know, that's voltage. Voltage. So voltage is actually not a force. Energy per charge is not a force. So that's a clarification needed. But it's an expression that hasn't changed, even though technically it's got some issues. But the real problem is we need to get a charge, such as this positive charge in a conductor, to move around the conductor to flow in the circuit so it can do work to light light bulbs and run your cell phones and computers and these kind of things. So we want it to move around the entire circuit, clockwise here, as I'm showing. So we want that to move around. The problem is, in order to get around this entire path, we know that at any given point it's got a certain potential and therefore a certain potential energy. And you know, if this is a perfect conductor, we know that potential is constant everywhere. But as we've also now seen, we actually do have an electric field that's required to move this around. But the potential at this point here, if this goes entirely around the circuit, the potential at the end has got to be the same as at the beginning. So those potentials have to be equal. Just like a waterfalls, you know, waterfalls downhill, and the potential energy and also the potential of the water is less at the bottom than at the top. So we need thermodynamic disequilibrium through weather to bring that water back up to the top via rain. And so you have to raise the potential and the potential energy of the water to get it back to the starting point. Well, we need the same thing here as well. For the charge to move, first we need an electric field, because that is what puts forces on the charges. So there's the electric field, but we know that in the direction of electric field, potential goes down. The electric potential always decreases in the direction of the E field. So that produces a problem. How do we get this charge to move around the path like this? It doesn't want to do that on its own, does it? The potential is just going to keep going down, 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 and that can't happen. Potential has to be the same in both places. So the solution to this issue, or this problem, is pretty straightforward. To get back to its starting point, it needs an external agent to shove it back there, basically. So we need to raise the potential, and therefore the potential energy, at some point. We have to raise it back up. As it loses that potential, we have to raise it back up again to get it back here. Well, that external agent, as I'm referring to here, is what's meant by EMF, or electromotive force. Some device has to raise the energy of the charge. The EMF, the energy per charge, has to go up because it's been going down as it goes around the circuit. So sources of EMF, batteries, generators, solar cells, fuel cells, thermocouples, those kind of things. You're familiar with some of that. And the source, those energy sources are just energy converters. They take chemical, light, heat, kinetic, and they convert it into electrical energy. So it's electrical energy that's manifested in our familiar electronic devices. So how does that EMF work and relate to other aspects of the circuit? Let's investigate that just a little bit more. So let's consider a source of EMF, and I will use EMF in the context of how we just described it, recognizing it needs some clarification. It's not really a force. In this case, we'll look at a battery. So we have a battery. It's a source EMF. And in the entire context of this discussion here, we don't have anything connected to it. So it's a battery sitting there, and there's no external circuit that enables charge to flow. So there's a battery sitting there on the table. Let's look at the internal workings a little bit. we have an electrostatic E field in a battery, E sub E, and that electrostatic E field points from plus to minus, as you would expect. So there's a separation of charges, the plus and the minus. That separation of charges produces that electrostatic E field. Charge separation is what it's associated with. But you might ask, where did that charge separation come from? Well, it actually came from the non-electrostatic E field. So we now define another E field. It's actually pointing in the opposite direction. We call it E sub n, non-electrostatic, and it's from the energy of the source. In this case, chemical energy is involved. Come on, stove. Gee. Stove back here roaring and snapping and creaking from expansion as it's heating up. We're expecting a snowstorm tonight, so let's get the house all toasty warm and ready. And then getting back to the topic here, an open circuit, we have, again, open circuit means that there's just nothing connected, battery's just sitting there. That non-electrostatic E field, as you see, which is something having to do with the chemistry of the battery, is equal to the negative of the electrostatic E field. Now this is pretty important that those are equal and opposite. If they weren't, there'd be a net flow of charge going across there. All right, so the magnitudes of both of those E fields are the same, so no charges move. And VAB, the voltage of A with respect to B, is equal to what we call the EMF. As we move across this electric field, we have a rise in voltage, and that's what we mean by the EMF of the battery. When it's disconnected, we could take a voltmeter and put it across here, see what that voltage is. That's what we call the EMF of the source. So what causes the electrostatic field to exist? The non-electrostatic EMF. Why? Because it's that which puts forces on the charges chemically to move ions across the solution and actually produce a separation of charge, after which, by definition, there's an electrostatic E field. So what it's caused by is a force, chemical, magnetic, other things, causing the charges to separate, resulting in the regular E field. So potential difference of a source is the work per charge of an electrostatic field, which is current dependent. The electromotive force is the work per charge of a non-electrostatic field, which is constant. It's the property of the source itself. So the chemistry of the battery produces this electromotive force. And the current dependency will be seen shortly. As we enable current to flow, it changes the condition inside the battery that we'll now investigate.